Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're gonna take a look at orbits. So let's go around it. So all you have to understand about it, it's Newtonian physics. Basically it's not quantum physics. It's very easy to understand, it's very calculatable. There is no magic quantum tunneling here. It's very simple. It's what we call classical physics, sometimes also referred to as Newtonian physics. Now many of you must have heard the story that apple fall on Newton's head, but I also heard a conflicting report about the story, so I do not know which one is true, but story that I have heard goes around like apple fell while he was looking at the moon. So problem was that when apple fall, he thought that why the heck moon is not falling, like earth is here, why the heck moon is not falling. And yes, it did happen in day. You can see moon many times in daylight also, but it's not very bright, so many times we flat out ignore it. So do look around, you will find moon during daytime. So that triggered his imagination. Is like, why the heck big thing that's supposed to be falling is not falling, versus apple that is small thing is falling. So things happen. So he devised a very clever experiment, what we call Newtonian cannon. Basically, if you have a earth and you fire something from a cannon, big powerful cannon, it will go around, but it will fall over time. It will fall. So let's say you didn't fire it fast enough, it will fall point A. You fire it bit faster, it will fall point B. You fire it bit faster. Now at some point you will fire it so fast that before it falls, the curvature of earth bends below it. So if it's going, trying to fall, the rate of its falling is basically slower than the slower would be wrong word, but basically the curvature of earth is preventing it from falling. Basically it cannot fall because earth itself is bending away. So that's what we call orbit. Now, of course, there are hundreds of things interacting here, like every celestial body, including sun, moon, and solar wind, and atmospheric drag, and everything. But this is the rough idea. If you fire something fast enough, it will fall. It is continuously falling, but problem is it cannot fall fast enough that it will reach Earth. So basically, Earth is like nope, 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 and that's why many times you will hear people saying this one: space station is free falling. Basically, you are not a place where you have zero gravity. International Space Station has 88% of Earth's gravity, but because it's in free fall, it's continuously falling, it always feels as 0 g. Basically, there is no gravity. The effects of gravity is gone. So be mindful of that. And it's generally when we talk about orbits, we are generally talking about large celestial bodies, as in Jupiter, Saturn, Uranus, Neptune, Mercury, Venus, and all that thing. And sun is also orbiting around Milky Way. Milky Way is not orbiting anything. So that way there are always things small and big. Small as in like small asteroids versus big things as in sun. There are a lot of things that are orbiting. It's a very common thing. It's found throughout the universe, throughout the night sky. And your size really doesn't matter. You can be a dust cloud and you can still be orbiting something. So be mindful of it. It does not matter about the size. So that's what orbit is. So what are the uses of it? Well, there are millions of orbit types. So let's try not to go into them. But you have to understand, each orbit provides a unique tool that you can use. Orbit itself is a tool. This is a very good graph that you can find, and I will try to link below, or try pasting a high quality here if this one is not reading clearly. Basically, the higher you go, the rotational period of your orbit will become slower. So basically, if you are orbiting very close to Earth, you are orbiting at roughly 20 minutes to 40 minutes. Your one orbit is taking 20 to 40 minutes. You go above, it takes 10. You go above, at certain point you reach 24 hours. That's why you see this is going up. So once you reach that perfect height where the orbital period is 24 hours, you reach a what we call geostationary orbit. Basically, if you look down from that satellite, you will see same thing on Earth continuously. Like that's it. So what do we use that for? Communication. Like all your TV direct to home, basically dish, if you see them pointing somewhere, that's what it's pointing to. That is geostationary satellite. When I say communication, I don't mean your phone call that goes through it or your internet. Basically TV, weather satellites and things of that nature, because the bandwidth is not that high. It's very good for broadcasting, however. So television satellites and slow speed internet is very primary use. Mainly is used for TV satellites. But you might be like, okay, doesn't that make perfect spy satellite? Actually, no, because there is something known as inverse square law. Basically, the further you are, the less light you get. That means if you are in geostationary, which is upwards of 30,000 kilometer up, you need a telescope to see on what's going on Earth. However, if you are at low Earth orbit, basically below 500, you need a very small telephoto lens. You basically need a normal size satellite. Now you might be like, okay, but doesn't it have non-continuous coverage? Basically the coverage will break. Yeah, but you can launch multiple of it, and it's cheaper to launch at that orbit. That's why spy satellites are generally at low Earth orbit, which you have to be mindful does not mean there is no spy satellites at higher altitude. It's just that if you want to do optical surveillance, it's generally preferred to be at low Earth orbit, because the Hubble telescope, the whole design of Hubble telescope is upgraded from a spy satellite which was at very high altitude. So you need basically like Hubble Space Telescope to compensate for that distance, not the atmosphere. The fact that you are 30,000 kilometers away, like the radial size, the size of Earth becomes so small, you need freaking giant telescope to actually do any real work. So there are heights of orbit. Each height will provide a very clear advantage and very clear side effect. Like for instance, in geostationary, your batteries need to be very small. So let's say you are doing TV broadcasting, you are receiving from ground station and you are broadcasting all around the world. Awesome. And you need solar power for that. Awesome. But here's the deal, you go through Earth's shadow for a very short amount of time, because the orbit is so long. Even though your receiving station, like basically the place you are broadcasting to, has gone during the night side, you are still in the sunlight and sunlight. So sometimes you can be as low as 1 to 5 hours of dark side you have to balance in whole day. So your battery size has to be very small. Now in compared to that, for low low Earth orbit, your battery has to be working at 50% of the time. So it's not like 5 hours in 24-hour day. It's basically 12 hours per day you have to run on battery. So be mindful of, there are pros and cons to all of this. And there are many types of orbit. Now the reason why everybody keeps saying about LEO, low Earth orbit, because that's the starting point. Be mindful of that. That's not the most useful, but that is the starting point of orbit. You can orbit lower than that, but because of atmospheric drag, you might as well need a nuclear engine to keep you aloft. And they have tried that. Soviet Union did try that, so I'm not making this up, they actually tried that. So for practical reason, we want to be as low as possible for ease of actually approaching. That's why ISS is so low. And another fact of that is what we call Van Allen belt. This is a belt where radiation, basically high energy particle, is trapped because of Earth's magnetic field. If a human goes there, they're dead. If electronics go there, they have to have compensation for it, from grounding circuits to make sure they have fault tolerant, to make sure they have redundancy against bit flip. There is a whole plethora of things that has to be done to make sure their electronics works, and humans simply cannot live there for long enough. So ISS is generally put so low that it's below Van Allen radiation belt. That's why ISS is so low, and keeping it low means the rocket does not have to spend so much energy to travel that far. So for this reason, ISS is very low. Like on this image, ISS is like barely off the surface. To give you a visual context, one is 500 kilometer and geostationary is 30,000 kilometer. And then there are other extreme types of orbit, which we call Lagrange point orbit. Basically, this is what we call L1, L2, L3, L4, and L5. Now, this is only happens when you have two body, one massive body, one smaller body. It will happen, Earth, Moon. It will happen. Generally, very prominent one is Earth and Sun. Now, basically, that means if you put something in L3, it will stay there. Now, be mindful, stability of these points are not equal. So if you put something at L4, it's not going to go away even if you fire thrusters. Like, of course, if you have big enough thrusters, it can be fired away, but it won't go anywhere because it's a stabilizing. Like if you put something there, even if it nudges off, it will come back. Now, same happens in L3, but it's forward and backwards direction. So, but if it goes left or right, or in this direction, yeah, it's done. It will lose that orbit. So all the points are not stable. That's why when you hear people say the James Webb telescope does not have life, that's what they are referring to, because it will be at L2. It has to have a propulsion engine, basically rocket engines, keeping it, doing the station keeping, because it's gonna move away over time. Now if let's say James Webb were put at L5, it would have lasted there for a very long time. Why they didn't do that? Distance is ludicrously far apart. So That's the whole point. So be mindful. We also use these Lagrange points for our satellites. So if you have solar observatory, basically you want to observe the sun, best point is L1. There are some satellites there. And if you want to observe further universe, we want to send things to L2, which will be James Webb Space Telescope. So these are orbits and their use. So let's understand satellite itself. Now LEO, as I already mentioned, that's why all the rockets are mentioned as LEO capacity. Like that's why you hear Falcon 9 can send 20 ton. Now that 20 ton is to LEO. You can't send 20 ton to geostationary. It simply does not have enough thrust to send that much to geostationary, that high. So from practical standpoint of view, all the rockets are always measured in LEO. Benefit of that is that you can easily compare. Side effect of that, sometimes you may get misleading result. So you may be thinking like, okay, Falcon 9 has 20 ton capacity, my satellite geostationary satellite is 10 ton, I can send it. You have to double check. They might have to boost the rocket engine, or they might have to let go of reusing the boosters to get that extra velocity. So it's helpful in one way, bad in another way. Now geostationary, as you can see in this image, each country gets its own basically band of space that you can see. Whenever you see that debris and satellite images, this slim ring that you see around the equator, that is the geostationary band. So basically each country gets basically cone of that band is dedicated to one country. You can't point like China cannot place a satellite that is interfering in Earth, India's geostationary orbit, nor USA can place something that interferes in there, not even spy satellite, because this region is very closely monitored by every country, and if somebody triggered a disaster there, let's just say it's going to kill everything, because most of the satellites are below it, including GPS satellites. So if any catastrophe were to occur in this orbit, basically geostationary, everything below is in danger. So for this reason, you can easily see every country gets their own basically inclination, as you will. So USA has 98 point that, and Japan has 140 degree east, India has 94 degree east. So for this reason, you get a specific degree. That's why each country gets their own DTH, direct to home service. Now there are two things you have to understand. If you are rotating with the Earth, like Earth is rotating like this clockwise, and you are going with this clockwise, it's what we call prograde orbit. Now if you are going against it, if you're like Earth is rotating this way and you're like, no, I'm going to go against it, that's what we call retrograde. We don't generally like to use retrograde. That means a bigger rocket has to be used for sending smaller payload, because you are fighting Earth's rotation. If you are going with Earth's rotation, basically that's like Earth is swinging you along. Now if you are going retrograde, you have to fight that, like Earth is throwing you away and you're like, I have to go back. So for this reason, most of the satellites are prograde. Generally only few for some reasons are retrograde. And there is one weird thing about orbits that you have to understand. There is one thing what we call its graveyard orbit. Now this orbit is above this geostationary orbit. Now above this, like 30 to 300 kilometer above from that, from orbital point, there is what we call graveyard orbit. Now you might be like, okay, why the heck we send things there in graveyard orbit rather than burying it underground, like basically sending it down? Two core reasons. First, sending it down means you have to create a very clear path. You cannot interact with any other satellite, because there are many satellites there. There is a 20 plus GPS satellites, 30 plus GLONASS satellites, 15 plus Roscom satellites. There are hundreds of satellite systems, weather satellite systems, and sun synchronous orbit satellite systems. So you have to create a path that is completely clean of any other satellite. So suffice to say, that's a kind of a hell of a headache. Now on top of that, that itself is not that big of an issue. However, the engines you require to deorbit geostationary, it's very energy intensive. The delta V, as they call it, the energy required to deorbit from geostationary is very high. That's why it takes a big rocket to send that geostationary. So to go from geostationary to basically graveyard orbit, it's a very small rocket thrust. It will fly, yeah, now it's at graveyard. But if you want to deorbit it, you have to fire a big engine for a very long time. For this reason, the fact that it requires very big and heavy delta V, we generally don't prefer the fact that we will try to slow it down and then make sure there is a corridor that's completely clean of every other satellite. And not every satellite has maneuverability. A lot of satellite do, but not every satellite does have that. And so far, one satellite collisions have happened where one navigation satellite got hit by an old defunct satellite, lot of debris. So for this reason, we generally prefer to just send things to graveyard orbit. Now, can anything come back from graveyard orbit? Unlikely, but it is possible. Let's say if a meteoroid or for some reason lot of solar wind occurred at very small period of time, it can push things down, and that would be a very bad day if that were to occur. So these are the orbits that you have to understand. Now there are also extra Earth, basically outside of Earth there are other orbits also which we are generally used for what we call low energy travel. Basically, if you don't want to use giant rocket to send a small payload to Mars, you're gonna use what we call home in transfer method. Basically, you're gonna use the Earth's orbit around the sun, not its spin. It's orbit around the sun to send your payload along. Benefit: very small rocket can send very large payload, relatively speaking, to Mars. That's how India got its payload to MOM. Basically, the MOM Mars Mangalyaan, we call it in India, but it's MOM if you want to derive it in short forms. It was sent using that. Consequence, it's ludicrously slow. That's why everybody keeps saying it takes 2 years to go. And this method also require what we call window. You have to find alignment that is just perfect. If you try to launch anytime you want, you can still go to Mars. It's not that, do not think that you cannot go to Mars, like if that window is not there. You can go there. You just have to use super large rocket to send super small payload. So to optimize that, generally we have a what we call window. That's why you keep hearing window. There is a window every 2 years. So in that window, you have to spend least amount of fuel to get the most amount of payload. But if you have very powerful engine, let's say very powerful nuclear powered ion engines, you can do that thing you wouldn't need this method. However, we don't have that technology yet. Now there are other orbits also like this, which we call comet orbits. Now they are generally done for advanced research and things of that nature, generally research of comet itself. That's why some satellites follow this, and Rosetta satellite and all that. So these are extra orbit that we generally call transfer orbits. Now let's talk about the most talked about topic in the internet, Kessler Syndrome. Now what you have to understand is, basically, if you increase the velocity, the power you get on impact doubles. So it's like you increase the speed by 10%, you don't get impact energy by 10%, you get 10 square. That's the horrifying part. And all these things that you see, these are traveling at minimum at 24,000 kilometers per hour. Basically 11 to 15 kilometers per second minimum, otherwise they wouldn't be in orbit. So at that minimum speed, even a small grain can cause very severe damage. That is caused by a very small pellet, and that's 1 inch thick aluminum, and it's just like boom, it's very big damage. So this is why everybody is so worried about it. Like, what if a collision happened? You don't need big things hitting you. It's not like where you have a pebble in a road and it hits your car going at like 300 kilometers per hour. It will barely damage your windshield. Like, of course it could crack it, but it's not gonna annihilate your car. But you get hit something as big as like let's say object that is weighing upwards of let's say 500 grams or half a kg, yeah, you're done. Like, that's like a nuke level energy output. So people are worried about it, and rightly so, because the energy is involved in these things, this junk. Now what this junk is made of? First, defunct satellites that were not at geostationary, but they did not have the engines to crash them onto Earth. Over time they will crash, but they will crash so slowly, like they have been there for, let's say, 20 years, 30 years. People are still waiting, come on, come down, because if you are very close to low Earth orbit, you crash almost in 1 year to 15 years. But as you go up, the crash time goes down and down, down and down. So at geostationary, if your satellite goes burst at geostationary and you can't send it to graveyard orbit, yeah, that satellite will be there for a very long time, and you can't knock it out. Like, we don't have the tech yet. And it's not that we can't do it. We have the physics ready, we have the rocket engines ready. It's just that to remove a satellite that costed 500 million to launch, you have to spend 800 million to actually go there, fire a rocket engine, and then slowly, safely, carefully move it. But as our orbits get more filled up, because there is a limited amount of space in what we call geostationary band, so we have to do this if there is a satellite that that cannot be sent on its own to graveyard orbit. So collision does happen. This sort of thing does happen. Do not think like it never happens. I already mentioned one old defunct satellite got destroyed by not old defunct satellite destroyed one functioning satellite. It happened. It's a common thing to happen. And this is an image of International Space Station from its collision point of view. All this red area is getting constantly bombarded. Now you might be like, okay, why the heck it's not getting destroyed? One very simple reason. Now, even though you get a lot of energy with this site of small size of collision, the ISS is specifically built with armors. Now, what is that? Armor simply means is basically they figured out like if they can only send 1 centimeter thick aluminum as due to their weight constraint, it is better for them to split that aluminum into two parts, one 6 millimeter, one 4 millimeter. So that way, if something hits it, because of ludicrously high energy, it shatters. Now, of course, there's gonna be a hole there. Now, because it has shattered and directionality, like from a pinpoint, it has went like more like a shotgun blast. The second aluminum sheet, which is only 4 centimeter thick, 4 millimeter thick, it can easily absorb it. So there won't be a direct penetration. And this was done. They tested it out. Okay, everything worked. And now in this International Space Station, the layer, the gap between those two aluminum sheet is filled with high quality Kevlar. Basically, it's a bulletproof. So due to this reason, they are getting bombarded. They are getting bombarded 24/7, but they can survive simply because they have armor. Now, on top of that, they are only getting bombarded by small object. That's why, like, high risk impact, when they say like small object, like a nail, what I'm saying about basically nut bolts that is falling off from upper satellites or defunct old rocket stages. But whenever there is something big, as I told you, like half a kg big, yeah, then they're gonna move this whole station. The station has what we call pizza box. Basically, that pizza box is always monitored. Like this whole orbit from above to bottom is always monitored, so that nothing big, like small things, is getting hit by 24/7, but nothing big, as in like there is a minimum size that it can handle. But once you exceed that size, let's say there is a whole second stage of a rocket coming to it, yeah, ISS is not going to withstand that it cannot withstand. It can withstand small things, but it cannot withstand a whole second stage crashing into it. It's going to be destroyed. For that reason, there is a lot of radar station, ground station stations on this itself station that are above satellites. They provide a sort of coverage where if they spot something that is big, let's say a second stage of a big rocket coming towards it, they're gonna move the ISS. They're like, nope, we're not gonna take any risk. It's just move that. And that gap is very large, so that's why it's look like a pizza box. The volume of it is look like a pizza box, so they move it around. And it's tracked constantly. So even if you see this many junk, not all of the junk is that big. So big one we always track, and small one we have to bear it. It's like we have to bear it. Like we have to bear it. Now be mindful. This thing one of my friend asked me, and it was quite a good question. If there are this many, like millions and millions of tracked debris, that means it's big enough to be tracked by radio. How the heck we can even send any rocket without it blowing up? The reason for that is the volume in space. Basically, the space in space is very large. So the volume of Earth is nowhere near the compare of the volume that we have in space, because Earth is only 6,000 kilometers. Okay, this gap is 30,000 kilometers. So as you can understand, the volume wise, it's very, very mind-bogglingly vast. To give you a context of this, think of it this way: oceans or sea have like ludicrously large amount of life into it, like fish, sharks and all that. But every time when you jump, do you get attacked by a shark or do you get attacked by a fish? Like most of the time when you take a jump into a sea or a river or an ocean, you don't interact with anything, because there is a lot of empty space between these things. Same happens here. And there are clusters of area where, let's say, when China attacked one of its own satellite, their cell satellite, they wanted to test out their weapon. It created a lot of debris. Now that debris is like a clumped area, because it happened from one source. That whole area has been evacuated. It's like, okay, there is this one clump going around the Earth, and every satellite is like moved away. So there are clumps, and rocket launches have happens where they take into consideration, okay, that lump is there, let's not launch when our, we have direct path to that. Okay, lumps passes at, let's say, 7 a.m, so let's launch at 8 a.m to make sure, like, it's far off. So there is a lot of space, that's why it's not happening. And big objects we track. However, if a runaway happens, which hasn't happened yet, thankfully, we're gonna lose access to space. The reason for that is, like, if big objects collides with another big objects, it creates enough small objects, the whole space gets littered by small objects. Small objects cannot be, tracked properly, and not to mention, if it's small enough and covers a large area, not in patches, like this whole area is covered, no rocket can go through. So that's what we call Kessler Syndrome. That's why it's not happening away, because the gap between the large chunks is very large, and small objects we can just withstand. But if two large objects, let's say two geostationary satellite or one graveyard satellite, for some reason gets deorbited or get hit by a meteoroid and bashes into a working satellite, big satellite, then it's all over for humanity. Humanity is going to lose entire space capability in fraction of a second, because if runaway happens, we can't track satellites. And not to mention, satellites cannot move, like, as freely as in shown in science fiction movies. They have, like, okay, I'm going to change my degree little bit. Even ISS, which has rocket engines, like, as in it uses the engine that is docked with Soyuz capsule, it does not have the, like, it's not Millennium Falcon. It still has a very limited range of movement, and because of the G-force limitation, it slowly does it. Now, if something big happens here, like, let's say in these outside orbit, you dead. You have to abort, you dead. Now, atmosphere will still protect us, nothing will get to us, but this is a very serious thing. So this was my presentation. I know it went a bit long. I hope you still liked it, and in that case, please leave a like. If you didn't, don't worry about it, you can dislike it. And I would urge you to comment what you want to see in the next episode of Rocket Monday. Please share amongst your friends and subscribe to my channel. And if you are free, press the bell icon. And as always, thanks for watching.